Well, good morning. I'll just start with the abstract of this thesis. You can see that the research that I'm doing is, although it's not in any formal process yet, it is definitely at a stage where it needs quite serious academic critique, and that's why I'm throwing it open to the community for this seminar type discussion. And secondly, because you can also see, if you take a moment to pause and read this abstract, you'll see that it is presenting some quite significant departures from standard model cosmology. And yet, it is mostly consistent with general relativity in all of the tests that I'm able to apply to it. It works quite well as a comparative form of general relativity. A research question that occurred to me a few years ago, looking at the physics of dark energy and dark matter and the evident flatness of the universe, I just want to make a point against that backdrop that it's still quite arguable that the universe has a spherical structure. Most of the overall details of our understanding of cosmology are that it forms a spherical symmetry. The Hubble expansion itself has its simplest description in a spherical type of expansion. The simplest types of models that can analytically resolve the expansion are spherical. Secondly, it's also true that the gravitational field, any form of gravitational field, is fundamentally spherical. Thirdly, the cosmological horizons, and there are a number of them, in the detailed descriptions, they are all essentially spherical. They're all physical equal distances in every direction from an observer, and in the relativity principle that would apply to any observer located anywhere in the universe. And my last point there, somewhat arguable, but actually turns out to be quite consistent in the mathematics, that you can describe co-moving coordinates as a system of ratios of lengths. It's a coordinate system based on ratios of lengths, and that, when I first came across the idea, immediately struck me as being a good description of an angular system. The ratios of lengths are angles. So I'm just making the point that we live in an arguably spherical universe, and yet the most recent developments in cosmology suggest that the universe is flat for a number of both geometric and physical reasons. We can see in the evidence of the distribution of thermalized regions in the cosmic microwave background that the simplest and most accurate description of that distribution is that the CMB is another type of horizon affirmed in the distribution of regions, as I'll explain. And secondly, that when we examine all of the components of density producing matter or energy in the universe, we find that the total sum of all of those components is exactly 1, or 1.001 plus or minus an uncertainty which possibly overlaps with 1, given those error bars. But there is no natural reason why it should be anywhere near 1, and yet the evidence is that it is. It's also true that the universe is incredibly dynamic. There is an acceleration that we've observed in the data from the Type 1a supernovae. There is the evidence of an acceleration, that the universe as a whole is accelerating outwards, not collapsing under the effects of gravity. So it's not dominated by matter, but by mysterious forms of energy which are still not identified other than as the idea of quantum vacuum energies. And that is still the most plausible explanation for what dark energy is, but it's not actually possible for us to calculate it yet. So it still remains a mystery as to why 70% of the universe has this mass equivalent. And lastly, it's also true that the universe is incredibly kinematic. The cosmic microwave background has a dipole, the major dipole of the CMB indicates a relative velocity of an Earth-based observer of about 380 kilometers per second, and that's at least 4 times faster than your typical intergalactic motion. So the actual peculiar motion of our entire galactic group, because it seems that all of the galaxies that we can observe nearby have or must have this common 380 kilometer per second velocity, and that's a complete mystery. It still remains unexplained in either relativistic physics or astrophysics at any level why we should have such a fast local group velocity. We need to know how we can reconcile these flat and spherical descriptions, because they're clearly contradictory in many ways. How is it that the universe can be apparently both spherical and flat? So a good question to start with might be, how can we construct a geometry, if we can even call it a geometry, that is both spherical and flat? And the traditional method, coming from general relativity, and you can derive this in other ways, is the Friedmann-Lemaitre-Robertson-Walker metric, which is a geometric, four-dimensional, expanding and dynamic model of the universe. It's fairly easy to understand, though, if you just simply start with what's known as a two-sphere. That is essentially a three-dimensional ball, like a basketball. Hold it in your hand, pick one particular point on that sphere and regard that as an observer such as you. So you're a two-dimensional astronomer on the surface of that ball. And looking out, according to the standard theory, the appearance of objects in near space, in local space, would have the geometric perspective. That is, they would appear to diminish in size with distance. And there's a simple relationship between the distance and the angle that's subtended by the apparent dimension, the size of an object, and that would behave in a simple linear way that things would diminish with distance. But because we are looking at what is a type of a sphere, that is quite simply in the same sense as if you drew some diverging lines from a point on a basketball. If you continue to diverge following ideal great circles on that sphere, those lines would reconverge on the far side. In a sense, it would mean that in far distant space, objects that we see from our reference frame here on Earth would look exactly the same as they would appear to an observer at some antipodal point. And at that point, at that distance, the laws of perspective would reverse. Now, it's possible to take that geometric result and derive a system of equations which include trigonometric components. That's this sine squared r component. That's the cyclic effect of trigonometry that leads to the conclusion that areas, visible areas around an observer, will increase up to some maximum point at r equals pi on 2 and then begin to diminish again. But the trouble is that there's no evidence for such effects that can be observed in the most recent cosmological data. And in fact, the best evidence from the picture here is from Lawrence Krauss's lectures. He always talks about this evidence from the boomerang experiment, measurements of the cosmic microwave background, the distribution of thermal regions in the cosmic background, occurring at a time only 400,000 years into the age of the universe. And that provides a natural length scale as distance and time are associated by the speed of light, and the geometry of extremely distant reference frames at that distance, the most extreme distance that we can see. And if you have a geometry that has a length scale that you can observe and measure, then it's possible for you to do calculations on that, for instance, to decide whether if you were to draw a triangle against that background, whether or not the angles of the triangle would add up to 180 degrees as they should in a flat Euclidean universe. And the best evidence is, according to these analyses based on that data, that that is the case. That cosmic microwave background radiation field is geometrically flat. So the best match that we have to our data is of a flat universe. And also, it's true, looking at the components of mass and energy in the universe, the rotation curves of galaxies and the gravitational lensing effects due to galactic clusters, we can see all of the components of the universe consist of matter, a mysterious component of dark matter, and another mysterious component of dark energy. And the physical effects that we can see of those different components all add up to a total that is as close to the critical density, that physically flat escape density, that would agree exactly with this geometric conclusion that the universe is flat. So it remains a question, how can we construct a geometry, if we can even call it that is simultaneously spherical and flat? So as a student, I set about basically rediscovering the metric, reinventing the circle, as it were, and doing a range of different types of universal volume calculations using different assumptions and testing different types of geometries. And I found that there are, in amongst the plethora of theoretical models that I saw, there were at least two ways that you can calculate the volume of a non-dynamic universe. And the first thing that I tried was what is recognizable as the Robertson-Walker metric, but I did it in a non-dynamic way. And I'll just assert, of course, that this is the wrong way. It gives you the wrong answer by an order of magnitude, which is still a surprisingly accurate result. And I did it in the simplest way possible without actually knowing that this is a canonical generic textbook result. Simply by taking, and this corresponds to the same method that you work out the surface area of an ordinary three-dimensional sphere, to work out the volume that's on the surface, in inverted commas, of a four-dimensional sphere, you take a projection of some internal angle, the projection being a sine function, a periodic function, which then will increase to a maximum area at psi equals pi on 2, and then reduce to 0 again at the far side, in exactly the way that the Robertson-Walker metric does. And that's not a hard job, really. In ordinary one-dimensional calculus terms, it leads to a result which is, again, a fairly textbook result, with these limits between pi and 0, assuming that pi represents some kind of a physical limit on the surface area of a sphere, then the result is the 2 pi squared s cubed, where s is the radius. Now, although this is a non-dynamic solution, I did assume that there are some kinds of kinematics that are acting, and I assumed what's known as the Hubble radius, s, as the radius of my sphere. And that's simply the distance that light can travel in the age of the universe, using an equation like s equals c t naught, where t naught is the age of the universe. And you can work that out. That actually works out as quite a large number, 1.3 by 10 to the 26 meters. It works better in light years. It's the age of the universe in light years is 13.8 billion years. And that results in a volume using this calculation. You plug in the figures and you get a volume of 4.3 by 10 to the 79 cubic meters. And that's wrong. It's too small by a factor of 10. The correct answer takes into account all of those relativistic dynamics and the scale factor of the age of the universe, how big it is at certain ages. Integrating through that expansion process with the right dynamics, you can find that the right answer, that the cosmological horizon, the radius of the observable universe, as it were, is a factor roughly 3.4 times the Hubble factor, and gives you a radius of 4.4 by 10 to the 26 meters and a volume on that basis of 3.7 by 10 to the 80 cubic meters, which is just 10 times larger roughly than 4.3 by 10 to the 79. So it's a tantalizingly close result, and when I first did this calculation, looked up what the correct result is, I was astonished to be anywhere near the correct answer. I wouldn't have thought that you could do this as a student trying it out in the simplest possible way. So I went ahead trying out other alternative geometries, and this is the one that I want to focus on. It is, again, it's non-dynamic. I'm trying to find Euclidean geometry in this system. I'm trying to find something which is flat and at the same time spherical. So before I go into explaining how I derived a metric based on that principle, I'll just point out that this picture that we're looking at here, I'm not suggesting that the universe looks like this, or that this is strictly speaking, or in any canonical geometric sense, what the universe is shaped like. But what I would say is that the universe, according to the data that we've got, does seem to have these spherical symmetries in the physics at least, and it also has these flat symmetries. So after a little bit of thought, having previously defined the metric by a projection of the angle onto a vertical, it still looks much like that, except the actual distance that I'm assuming, being that the distance out from the observer here at O, I simply used not the sine projection, but the arc length of that radius S on that angle psi, which the arc length is a very simple formula in geometry. It's simply R equals S times psi. Now, that's significant because as psi increases, as you allow psi to develop or evolve, or as you look further out into space, the angle that you're talking about, psi, must increase. And if you're saying that the distance to that point is simply an internal radius times that angle, the internal radius is a constant and the psi continuously increases. You're saying that that distance continually increases, and any measurements that you make on that, such as the surface area of a representative sphere at that distance, will also continue to increase. So I started by taking an element of volume. The area of that sphere is an elementary volume when you multiply it by a small increment of distance in that direction. And the formula is pretty straightforward. When you look at it, I'm taking the length S psi, squaring it to provide a square of a radius, multiplying 4 pi r squared, essentially, times an increment of length, which is an increment of volume. And reduce a few things algebraically, and then with the calculus again out to a maximum limiting point of psi equals pi. That's an even easier integration. It's simple polynomial integration. The result is psi squared d psi, which integrates to psi cubed on 3. And that actually is the same as the Euclidean volume of a sphere of radius pi times s, which is exactly this length here on half the circumference from the observer all the way around to that antipodal point. Now, when you put the numbers into that, I'll just jump down to where I actually do this calculation. If we take the actual radius that we're calculating for that distance pi s, r equals pi s, that's pi times ct naught, where before on the previous page we had r is equal to 3.4 ct naught. Here it is 3.14 ct naught, which is a very close approximation to the distance of the particle horizon. And when you plug that into this actually linear Euclidean volume formula for a radius of that size, you get a result which is within a standard model volume of the observable universe. I get 2.9 by 10 to the 80 cubic meters compared to 3.7 by 10 to the 80 cubic meters. So that's a surprisingly consistent result within 5% of standard model, and yet, as I said, it is completely non-dynamic. I haven't assumed any dynamics. I've just assumed the kinematics. S equals ct are the only dynamics I have here, and they're not really dynamic. There's no acceleration. It's simply a linear, in time, constant rate of increase. So this is something like V flat, but still not fully Euclidean, but volume, of a sphere that has that radius pi s. And also, when you look, I'll just clean up the page here a bit, when you look at that r equals s psi, radius s is increasing according to t, if you work out the velocity of some referent distance, the velocity of a distance r, capital R, being equal to dr dt, the rate of change of r with time, combining these two equations in a simple first-order differential equation, essentially, you get that the velocity is phi times the speed of light, c. And when phi is greater than 1, which is an angle here at about 60 degrees, anytime phi is greater than 1, then the recession velocity is faster than the speed of light. That actually accords quite well with general relativity. We know, as a matter of observational fact, that the galaxies that we can see at very great distances, although they're affected by the recession velocity so that they're redshifted, the actual velocities at those distances must be greater than the speed of light. But the metric does increase monotonically with distance, and we get a local flat perspective as that angle increases to infinity. And there is this very unexpected agreement of the kinematic geometry with the advanced physics. The next step in any physical investigation really is to examine the energy of the system. In other words, to solve the Lagrangian, as it's called in classical physics. Working out the kinetic and potential energies that are involved in this expanding spherical flat space is simply a case of doing that same kind of volume integration, but adding in some kinetic and potential terms about the distribution of matter, the way mass generates energy in the form of kinetic energy, and if it's gravitationally bound, then it's also generating gravitational potential. And I'll focus on the left-hand side of the page to start with, where this is the standard model derivation, or a simple description of it, where we have effectively a three-dimensional view of the universe from an observer's centered point of view. We can imagine that all of the matter that we can see arranged in space around us, it doesn't necessarily need a spherical reference frame. That's simply an integrative kind of a framework that we're using. But the further away we look, the more we can see that the universe is expanding. And it does so according to something I've mentioned already, the scale factor. The scale factor really is just the ratio of lengths. We consider the distance to some point as it is at the present time. We could call that a coordinate distance, call it r sub c. And if we imagine further back in time, this small red circle I've drawn here is an image of the present universe as it might have been several billion years ago. It was smaller, it was denser, and the simplest description of that, given the geometries we can see in the Hubble expansion, is that every physical length, r sub p, in comparison to the present coordinate length, is simply reduced by a scale factor, which is a constant for any particular cosmological epoch. Any particular period in time has the same scale factor. And it's possible to work with that scale factor in fairly simple ways to work out what the recession velocity is. And it was Edwin Hubble, of course, who realized that there is a recession velocity in the universe, so the galaxies seem to be expanding away from us at a rate which is proportional to their distance, and the proportionality constant has come to be called capital H. Still on the left-hand side, using those results from either a Newtonian or a general relativistic perspective, you can work out, if I can jump down to here, is by taking Newton's gravitational law, this derivation in a few steps leads you to the construction of a critical density. And there's a formula for that. That's the actual formula that comes out of general relativity, and you can derive the same result from Newtonian gravity. It's essentially the density of the universe at which escape expansion is possible, that the universe will continue to expand, decelerate under the effects of gravity. Realize that there would be only one particular unique density at which that could happen without subsequently collapsing back upon itself. So that's the critical density. Now, on the right-hand side of the equation, I'm trying to show how I take that kind of standard model derivation and produce results which also give a critical density in some form. And all I've done really is added one space dimension to my expansion. What I've really done here is I've taken this picture of expanding matter and I've spread it onto the surface of one of these putative four-dimensional spherical structures. If I allow that then to expand dynamically, then I can take slices through the universe and say that there's not only an element of volume but an element of mass at that point, and if there's a recession velocity, then that mass should generate a kinetic energy, and if that mass is gravitating because it's mass, then there will also be potential energies that are derived. Now, I've got to point out though that this, because it's expanding, time is an important dimension. If I've added an additional space dimension in order to describe this process of expansion, and if I'm saying that that is actually a space dimension, in conjunction with time as a fourth dimension, that must be a fifth dimension. And I had a target here. One of the original solutions from general relativity is the Cosmological solution, which very surprisingly, based on a five-dimensional assumption, was able to derive not only the equations of four-dimensional general relativity, but also the equations of electromagnetism. And that's a fairly profound unification that was not successful. The Cosmological solution is not the standard model solution. We've gone well beyond that, but it's still a great mystery as to why a five-dimensional solution should do that. And then within that, given that I know how to work out the recession velocity and the distances and the effects of kinetic and potential energy, that I could simply write those equations down and trying to solve the Lagrangian by identifying the equations of kinetic and potential energy. And that, I've actually got that detailed integration process set out on another page that's coming. And so you'll be able to see where these results come from. They're both fairly strange and complex looking equations. They both have this integral factor of psi to the 5 on 5, which, if you make a ratio between these two quantities, the kinetic and potential energy, that psi to the 5 on 5 cancels and leaves you with the result that if in some dynamic circumstance, say if the density was equal to the critical density, then the kinetic energy should be equal to the negative of the potential energy. That's one of the standard results from gravitational physics, that at the point where an escape velocity is just possible, it's because the kinetic and the potential energies are exactly equal and opposite. They cancel. You can form a ratio between these two quantities. And in my case, having gone through this process on an integrated five-dimensional framework, I found that the critical density is predicted as being 3 divided by 8 pi g, which looks very much like the general relativistic result, but it's multiplied by not h squared, but, clean up the page again, not h squared, but c squared on s squared, which seems to suggest in this geometry then that the Hubble constant can be described by the ratio of the speed of light to the Hubble radius, and that of course is an aspect of standard model cosmology. It surprised me though, and I set about trying to establish that that could be an acceptable, is that if that's a valid conclusion, that this is some form of the Hubble constant. Because if it is, it means that this is also some valid form of the critical density, and therefore that this is some valid form of a general relativistic solution. So I started to suspect that what I had was some solution to the equations of general relativity. I really had to establish that this Hubble parameter was something that was valid, that I could take that as read. So finding or reinventing the Hubble parameter, again I started with the recession velocity, combined it together using those forms of the dynamic form of the distance, r is equal to psi times a Hubble radius. You put those two things together and you find that the recession velocity is equal to c times r on s. Rearrange that slightly to make it c on s times r. And if we are saying that the recession velocity is proportional to the distance, whatever the function of proportionality is by definition the Hubble constant. I wasn't satisfied with that though. I tried looking at this in a number of different ways. It's settled on a model based on special relativity. And this is a special relativistic space-time diagram with a light cone. And when I took that out to a larger scale, at the universal scale, I'm imagining that flat local space in special relativity will acquire a curvature. When you allow that to expand out to the full scale of the universe, then the actual light cone also develops a curvature. But within that curvature, certain principles should still hold. For instance, any small element of distance, dx, within that light cone visible space, should simply be a distance that is travelled at the speed of light in some short period of time. So dx equals c dt should still work on that curved light cone. But because of the curvature that it's developed, there is an additional geometric interpretation of that small distance dx, and that's simply to take the small angle theorem again to say that there is a radius, a Hubble radius at some previous time when the universe is smaller, times some small element of angular metric, d psi. S d psi is equal to dx is a valid geometric description of how that would work. Which gives us two equations, s d psi equals c dt, and when you rearrange that for d psi by dt, the angular velocity of a photon on the light cone would work out as this factor c divided by s. Now that was incredibly suggestive, and I was able to use that in a different sense, comparing that d psi dt being equal to c on s. That's equal to a rate of change compared to the actual value. Compare that to the definition of the Hubble constant being the rate of change of the scale factor to the actual value of the scale factor. And with a few simple manipulations, I'm able to show that that does reduce quite plausibly and convincingly that this value c on s is the Hubble parameter, and that's a variable Hubble parameter going back into past times when the Hubble radius s was some smaller value. But I hear you say, if you know this subject reasonably well, you'll know that the equation h naught equals 1 on t naught is the solution for an empty universe. That's a universe that has no matter or mass or energy in it, so that if it is expanding, because it's not subject to any gravitational dynamics, it would expand at a constant rate. So this term a dot, the rate of increase of the scale factor, would become a constant. It would be simply equal to whatever the increasing rate of the scale factor was in the beginning, a dot naught. It also suggests that a double dot, the acceleration of the scale factor, is zero, and therefore there's no dynamics. And that's highly implausible. That is completely against all of the principles that we understand from standard model cosmology. Whether you're in the old school, still believing in a matter-dominated universe, which should be decelerating, perhaps ultimately to a zero rate at infinite size, which would be represented by an escape velocity, or if you're convinced by the supernovae, the lambda CDM model suggests that the universe is accelerating, and in comparison to either of those conclusions, this idea of a constant rate of increase with zero acceleration is just a straight line, and that's kind of boring in terms of modern physics, but it leads to this result. You can simply boil those factors down and show that it reduces to h equals 1 on t. And that's a bit challenging, really, because a zero dynamic implies that there is no acceleration at the cosmological scale, and this can only arise if there's no gravitation or if there is no mass. So zero gravitation or zero mass. But a critical density universe that's flat and in uniform isotropic homogeneous expansion has these equal opposite energies, the kinetic and gravitational potential energies. And we can consider those in general relativistic terms. We can consider any form of energy to be a type of a relativistic mass equivalent. The equation, I haven't even written it here, E equals mc squared, reduces to the proposition that any form of energy will reduce to a type of relativistic mass. And you can find that mass simply dividing by c squared, by inverting that equation. But if the total energy, because the kinetic and potential components of the energy, which are the dominant large-scale components of the relativistic expansion of the universe and its relativistic contraction upon itself due to the effects of gravity, if they are equal, then the relativistic mass of that system is going to be zero. So in a flat universe, then, the cosmological acceleration can be zero, and it's a reasonable proposition which at least fits with the other quite outlandish propositions that this thesis makes. I will say that this effect is interpreted as inertial as opposed to non-dynamic. I know that historically, for instance, the Kaluza-Klein solution of general relativity was rejected ultimately because it's non-dynamic. It has no accelerations on the large scale, or rather the metric of the x5 dimension is not a function of the x5 dimension. It doesn't change with its own expansion. for instance, a free-falling observer, someone in orbit around the Earth, an astronaut on the International Space Station, experiences no acceleration. There is no sense of gravity. You're in complete free fall. Even though you are falling around the planet, you're still not subject to any sense of gravity. And that, of course, is the equivalence principle in general relativity. I'll just point out, though, that I've said something which is quite non-canonical in general relativity theory, that there are these relativistic mass equivalents of the expansion gravitational energies. And there's a big question mark attached to that as to whether that kind of proposition is valid. And, again, I hear you ask, I'm anticipating what some of the questions might be. If there is no dynamic, that is A double dot is equal to 0, that really flies in the face of quite a lot of the evidence. How can this explain the observed acceleration of the universe that we can see in the supernovae type 1a data due to dark energy or vacuum pressure? How can this non-dynamic or inertial solution explain that observed acceleration? First of all, I find that there are redshift effects. The redshift is simply a function of the scale factor, and I find something very similar to that. Secondly, there are all sorts of asymmetries in this system, and they seem to center upon the role of the inverse square law. And at the critical density, it has an inverse square law built into it, because it's h squared in the critical density, and we've decided that h is equal to c on s. That has an inverse square of the Hubble radius in the denominator. And that's kind of paradoxical, because you expect a density in an expanding system where the volume is increasing, then the density should decrease by an inverse cube law. And that doesn't seem to be the case. And it does seem to be the empirical fact that the universe is expanding according to a critical density, and therefore it's behaving by an inverse square law rather than by simple volume dilution by an inverse cube law. And that critical density produces an overdensity, which predicts that there's a creation, an additional creation of mass, and that can only be explained by its vacuum pressure and negative pressure, which provides a negative component of energy, and those two things can only coexist if they cancel each other, so that this universe can expand forever, so long as it cancels itself out down to 0. The third point is that there are a number of different types of geometric components of this model. There's a scaled area that you can work out quite well, and the scaling of those areas do seem to have an effect on the apparent magnitude, that is the brightness of standard candles. I guess this will have to come down to part 2 of this lecture series, because it's a relatively advanced analysis, and I'll get to that. But the main one that I want to start with to finish today is that these relativistic mass equivalents of expansion gravitational energies, if we take them seriously and assume that within this system of propositions that they exist, that those gravitational and expansion energies can explain quite a lot simply by themselves. What I found is that these kinetic potential energies of gravitational expansion at critical density produce mass equivalents that are equal and opposite, but also dynamically significant in a number of ways. First of all, the most significant thing about these potential and kinetic energies is that they're actually about 3 times larger than the critical density. And that isn't hard to do using the same results that I've already set out. You can work out the total mass of the universe based on the assumption that it's got critical density, multiply it by the volume, leads to a total mass c squared pi cubed s on 2g. Now s is increasing, and that would have to mean that in this model the mass is increasing. Or you can convert that to time if you like. So simply by taking s equals ct, you get another c factor, becomes a factor of c cubed times pi. So c pi being the maximum recession velocity at the co-moving coordinate psi equals pi. And that has to be inflationary because t is increasing. So as we proceed towards critical density, the mass at that critical density increases with time. And of course that leaves a huge question. Now when I take those kinetic and potential energies that I've derived before and reduce them down to the same terms as a function of time, I find that they're very much like the mass, the critical mass, except that they're this factor 3 pi squared on 10 times larger. Both of these kinetic and potential energies at critical density are proportioned as about 3 times larger than the mass of the universe. So that's surprising. It's surprising that a mass can produce a mass equivalent which is 3 times bigger than itself simply by engaging in kinetic and potential reactions within an expanding universe. So critical mass produces these dynamically significant relativistic mass equivalents, and it occurred to me at this point, and the light suddenly went on, that possibly all forms of mass, including the mass equivalents themselves, have expansion energies. If you're generating a mass equivalent on a manifold of a distribution of real baryonic matter, those mass equivalents, they're also going to be expanding with the universe, and also because they're mass, they're going to be gravitating, and so they're going to be, by engaging in expansion and gravitation, they're going to be generating kinetic and potential energies, which in turn have a relativistic mass equivalent interpretation. And these things are highly dynamically significant. In other words, if you took the simple baryonic matter of the universe, the actual real luminous matter of hydrogen, helium, and all of the heavier elements that we can see, that should, in expansion, produce a combination of the potential energy due to baryonic matter plus the kinetic energy due to baryonic matter. Or if you include the dark matter, the evidence of dark matter is in the rotation curves and the accelerations of galaxies and galactic superclusters. If we say that the actual mass of the universe is both baryonic and dark matter, I've just introduced this symbol here, looks like a combination of a B and D representing baryonic and dark matter, that would have both potential and kinetic equivalence because that baryonic dark matter is engaging in gravitation and it is engaging in the overall acceleration. And it occurred to me as a hypothesis that those terms, the baryonic dark matter and the resulting kinetic and potential mass equivalence of the baryonic dark matter, could add up to the critical density. So this was a point that I got to, that the baryonic matter and dark matter in expansion produce these critical mass equivalents as a way of explaining why the universe could possibly converge on critical density, that there'd be some kind of a feedback into the nature of what dark matter is and indeed what dark energy is. So my hypothesis with that light going on brighter and brighter was to think that if density consists of 5% matter, 26% dark matter and 69% dark energy, could it possibly be that the dark energy term at least is in some sense related to the kinetic energy of this expansion of the dark matter? In other words, my hypothesis is just the density of the kinetic component, the relativistic mass of the kinetic component of baryonic dark matter is equal to the density of the vacuum energy or the dark energy. As a hypothesis, it seemed like probably at the simplest place to start, rather than making hypotheses about what both potential and kinetic terms were. I simply wanted to combine these ideas in a way that would allow me to calculate what that kinetic energy might be, and then compare that to the known value of the density of dark energy in the universe. And to ask the question, if I was able to produce these results, would they increase with time, providing some kind of at least a mathematical explanation for why the critical mass increases with time? Or, in other words, to reduce it to a research question, is dark energy a form of expansion kinetic energy? And it turns out that that was not hard to do, because I've got a simple linear equation consisting of baryonic dark matter, and I know how much there is of that. It's about 31% is what I'm expecting that to be. There's some unknown proportion of potential, and I actually at that point didn't know how to interpret what that might be, and some proportion of kinetic, which I was supposing would be representative of dark energy, and that this should equal, as a linear sum, the value of critical density. And I also, of course, at this stage had some equations for the kinetic and potential densities of relativistic mass equivalent. All I've got to do is take a particular density, there it is rho, and multiply it by these factors, and for the kinetic energy it's multiplied by the cube of the radius. For the potential energy, the same density has to be squared, as we saw, because it has two mass terms involved in the gravitational potential relationship. And these two equations I was able to substitute into these terms for the potential and kinetic energy density terms, which means that the whole thing reduced down to just one unknown, what this rho BD is, because there's rho BD here, there's a function of rho BD appearing here, and another function to the square of rho BD in here. So we'd have a constant term, the critical density being constant throughout the universe. We'd have a linear term, the kinetic energy is proportional to the first power of the density, and there'd be a square term where the potential is proportional to the square of the density, and that obviously is a quadratic equation, and that's exactly what it turned into when I wrote it down in full. And we'll have a look at the details of that. But the result is, given that there's just one unknown, this baryonic dark matter density, I found that the solution to that from this quadratic equation is 0.217 of the critical density. Now that's not 31%, but this other potential term was 14%, and if you add that in, it goes close to 30%. And the kinetic term, which I'll show you how I can derive this by getting this result here, I'm able to plug that result 0.217 into either of these two equations and get results for what the corresponding potential and kinetic energies are. And the kinetic energy worked out at 0.643 times the critical density, when I know that the correct answer for the density of dark energy, the density of the vacuum energy, is 0.69. So that's within 4.7%. And here, I've already mentioned this, if you take 0.217, 0.14, you add those together, you get 0.357, and that also is within that same 4.7% of the density of gravitational matter, including both baryonic matter and the inferred dark matter. So this was hugely encouraging. You can imagine getting within 5% of the correct answer. That at this level of analysis suggested to me, all of the lights started going on, it suggested to me that dark matter itself could be some form of potential energy, because I'd had to take this potential result, 0.14, and add it to my assumption of the baryonic dark component in order to come up with a result that looks anything like the standard model. So the next part of this set of questions was, is dark matter a form of potential energy? And how could that be? If we try to imagine a universe of just baryonic dark matter, which is expanding outwards and also gravitating upon itself, there's going to be kinetic and potential terms within that. My equation here is relatively simple. It simply assumes that all of the energies that are associated with baryonic and dark matter would come out in that term, which worked out to be 0.217. So that term, that value 0.217, should contain a small proportion of kinetic energy. In other words, the baryonic dark matter component includes all of the mass equivalents of the galactic and intergalactic matter and the process of expansion, and I should also say the process of gravitation. So that would include the mass equivalents of the kinetic energy at the filament void scale. That's the scale of the intergalactic large-scale superstructure of the universe as a system of voids and filaments between galactic superclusters. So the expansion energy of that large filament void structure would include all of the kinetic energy that we identify with dark matter. It does result in an increase in the kinematics of the rotation curves of galaxies. So there's a lot of excess kinetic energy, which I then, in a hypothesis, assumed could be found by subdividing that baryonic dark matter to locate the missing dark energy. And I'm just looking for a missing 4.7%. So my hypothesis was that the baryonic dark matter consists of 4.8% baryonic matter, and we know that from our astronomical studies. We can measure that from luminous matter, essentially, plus 4.7% of this putative kinetic mass equivalent of baryonic matter, which, because it's a kinetic, equivalent to the kinetic term that I'd already derived, which I can see corresponds to dark energy, that kinetic term should in some sense contribute to dark energy, which would leave only, if this still adds up to 0.217, that only leaves a remainder of 0.122, which is going to be the potential component of the expansion and gravitation effects of baryonic matter. So you can subdivide that baryonic dark matter equation, if you like, down into a detailed baryonic matter solution, which shows you how all of these different terms add up. And we're actually hypothesizing really that there's a kinetic and potential relationship of the physics at the scale of the filament void superstructure of the universe. And how can I test that? If I take those proportions of potential to kinetic, there's a quite well-known theorem in gravitational theory called the virial theorem, which simply states that the ratio of the potential to the kinetic energy of any gravitational system will be equal to exactly 2 when that system forms a closed orbit condition. So the moon in orbit around the Earth, the virial ratio of the moon to the Earth is exactly 2 because it's in a perfectly stable orbit, plus or minus small fractions for the fact that tidal effects and everything else are causing the moon to drift away from the Earth. So none of this is ideal in any sense. It's, as usual within physics, a certain amount of uncertainty around that figure. But when I take these two figures, the potential and kinetic assumed components of the filament void superstructure, that works out as 2.6. 0.122 divided by 0.047 is 2.6. Now that means that there's more potential in this system than in an equivalent orbital system. And in astrophysical terms, that means that that system is still undergoing gravitational collapse. The whole structure of the filament void superstructure is in fact still collapsing. As it expands, it's also differentiating into larger and larger voids, which interstitially separate smaller and smaller regions of intergalactic medium. The filaments that extend between the galactic superclusters, clusters, and the galaxies themselves. So while the filaments are partly expanding, they're also partly recollapsing while the voids expand in between them. So you'd expect a virial ratio to be greater than 2 because this system is still collapsing. So that corresponds quite well to what we know about the behavior of the filament void intergalactic medium. It is still undergoing gravitational collapse. And also, it's true that these baryonic terms that are defined are the galactic and intergalactic baryonic density. So this would be the density of the intergalactic medium, which is a known astronomical figure. So if we take that ratio, 0.122 to 0.047 being equal to 2.6, and we've got these two equations that we've derived for the kinetic and potential relativistic mass equivalent terms based upon, let's say that it's unknown for the sake of the exercise, intergalactic density, the density of the intergalactic medium, will behave just like any density in terms of its gravitational expansion effect on kinematic mass equivalence. And there's that factor of 3 pi squared on 10. It's the simplest part of this theory is that to work out a kinetic relativistic mass equivalent, you simply take the corresponding density, multiply it by 3 pi squared on 10. And to find the corresponding potential relativistic mass equivalent, you've got to take that density and square it before you multiply it by 3 pi squared on 10. And it also has this critical density factor, and you'll see that when you go back and look through the details. This formulation is quite important at this point, because when we form a ratio, the potential to the kinetic, those two 3 pi squared on 10 factors cancel. It just leaves us with a squared density in the numerator and a density in the denominator, and that's going to cancel down to just the density. And it leaves the critical density in the denominator. So it's actually saying that the density of the intergalactic medium is 2.6 times the critical density as a prediction of the matter density of the intergalactic medium. And that actually turns out to be correct. If you look through the literature on this, it's quite a variable figure because you've got to choose what your reference is. Between the voids and the filaments, there's regions of space where matter is simply becoming more and more diffuse out into an almost perfect vacuum. So there's no single hard and fast figure for the density of the intergalactic medium, but there is an average, and the average has been measured by a range of different types of studies. The interception of light by the intergalactic medium tells you quite a lot about its density, and there's an overdensity in the intergalactic medium in comparison to the average density of the universe, a rho b, which is one of the components of our equation. So we're looking for a figure that's something like 54 times rho b, which is in between 10 to 100 is the typical range of estimates of the baryonic overdensity in the intergalactic medium. And that's exactly what we get. If we take 2.6 and to convert that from critical density terms to baryonic density terms, we've simply got to divide by the proportion of baryonic matter compared to critical density. And 2.6 divided by 0.048 is 54. Close to the center of the distribution between 10 to 100. It's as close as possible without actually being 55. So by this stage I was quite convinced, and I was able to say, okay, our hypothesis then suggests that the actual kinetic energy, the total kinetic energy due to dark matter, is the term 0.643, which comes out of that original formulation, the quadratic formulation of this hypothesis, plus that component that I've identified simply by dissecting it according to these analyses. And I'll just say this set of results would account for the recent evidence that the early universe, the distant galaxies that we can see, the evidence is that they are less affected by dark matter in their rotation curves. They seem to behave in a more natural way, as if their gravitation is simply due to the physical baryonic matter which is present in those curves. So it appears as if the dark matter accumulates in exactly the same way, or plausibly in a similar way, to the accumulation of dark energy. As the volume of empty space, the volume of the vacuum increases, then the proportion of dark energy in the universe increases and accumulates. This hypothesis seems to be suggesting that dark matter also accumulates, and that would have an effect on the way early galaxies that are visible in the most distant universe would be less affected by dark matter, because it hasn't actually accumulated to the value that we see in the modern universe.